Welcome to a lesson with Dr. Powell. In this video, we're going to look at how we can define the six trigonometric functions: cosine, sine, secant, tangent, cosecant, and cotangent by using the idea of similar triangles. Now, if we have a right triangle, so we have a right angle here, and we know what the other angles is, theta, then of course the other angle will be well determined because all the angles add up to 180. Now, that any triangle that has those exact same angles will be similar to this one, meaning the ratios of sides will be the same. Like this side to that side will always be the same, or that side to that side, and so forth. In particular, if we know, amongst all these similar triangles, if we were to take like one of the sides, so let's suppose hypotenuse. So this hypotenuse is 1. Maybe we'll take a hypotenuse of 5. Maybe we have the exact same angles. We have a theta, and so imagine this is a bigger than this guy, but we're just not drawing it to scale. But just imagine this hypotenuse is 5. Then the ratio, let's see. In fact, the ratio from 5 to 1 is going to be the same thing from here to here. So this side length is going to be 5 times greater than that one. This side length is going to be 5 times greater than that one. Of course, we're using these funny symbols here, right? We're just using this symbol here. What is this? This looks like sin of theta. It's sine. We pronounce it sine, spelled S-I-N-E. And this is a function of theta. So you have, but we're using a word here, but it's a function symbol. So we're inputting theta and we're outputting something. Okay, what are we outputting? We're outputting a side length. It's a side length that relates to what this side length would be if this angle were theta here in this triangle, if we have a 1 right here. And what I'm trying to say right here is that these side lengths are going to be well defined and well determined if all we know is 1 and theta. If we know theta, and we already know the right angle, we know that angle, which means we're dealing with a similar triangle to where we're dealing with all these angles being what they are. And amongst all the triangles that have those exact same angles, only one of them will have a 1 on the hypotenuse because of how corresponding ratios are between those triangles. So if only one has a 1 here, and that's actually going to determine the whole triangle. If I know all the angles and I know one side length, I should know what the other side lengths are. The other side lengths will be well determined. And so we can use sine theta for one of the for the side length that's opposite the angle theta, and cosine for the side length that's adjacent. We call this adjacent, meaning next to that angle. That's not the hypotenuse. So we can define these angles, sine theta and cosine, in that way. Now, what if we move this 1 to other sides? Like, what if it was on what we call the adjacent side, or the side next to the angle that's not the hypotenuse? Then we can give names to these other sides. This side we can just call tangent of theta. Now, of course, it's going to be well determined. It's going to be a well-determined number here for a particular theta. But notice how it depends on theta. If I change the angle theta here, I'm going to get a different length. So this length right here is going to be a function of theta. That's why I write tangent of theta. And it is well determined if I know this, and I have that side length here. Then this will be a well-determined number. Maybe I don't know what it is exactly, especially if this is arbitrary, but this will be a function tangent of theta. Likewise, this is a function secant of theta. These are abbreviations, but writing this out, if you want, we say tangent. This one, we say secant. For cosine, we say cosine. Similarly, over here, we have a similar triangle. And if we have a 1 in this position, then we call this side length the cosecant, and this one the cotangent. Notice that it's like or copanion to this one, if you will. Instead of tangent, you're doing cotangent. If you flip across from theta between opposite and adjacent, sometimes in trigonometry we use a prefixed co to denote that. So in tangent here, but now we're going to say cotangent on this side, and then since we're the flip version, we're going to say the cosecant here. Cosecant. We just kind of put a co in front of it here. Cotangent. So loosely speaking, you can think of these functions simply as relating to certain side lengths. If you have an angle and you know one of the side lengths is 1. 1 here, here, here. In this particular case, all right, for instance, what if this side length was 5 and you have theta? Well, you know that this side length right here is 5 times 1, so this will be 5 times sine. So this side length will be 5 sine theta, and this side length right here will be 5 cosine theta. Similarly, if you had a situation like this, maybe you had the angle theta as you have here, but maybe you have a 5 here. How would that go? This would be 5 tangent theta. This one would be 5 secant theta. Now, using definitions like this are very handy for application problems when we're working with triangles and trying to get different sides and formulas and functions that relate different sides. It just makes things a lot simpler and crisper, and I'll show you some examples of that in the next video. If this side length is 5, then this side length right here would be 5 cotangent theta, and this side length would be 5 cosecant theta. Okay, and of course, assuming that's a theta and that's a right angle. All right, and in the next video we'll look at some more examples of this. Kind of introduce the idea of how we can define these functions in that way, and we'll see how we can use that when we're looking at triangles in the next video. Thanks for watching.